Day 11, seating system. Your plane lands with plenty of time. Oh man, I feel a sneeze coming on. Okay, I think we're good. Your plane lands with plenty of time to spare. The final leg of your journey is a ferry that goes directly to the tropical island where you can finally start your vacation. As you reach the waiting area to board the ferry, you realize you're early, so no one else has even arrived yet. By modeling the process people use or abandon their seat in the waiting area, you're pretty sure you can predict the best place to sit. You make a quick map of the seat layout, which is your input. Seat layout fits neatly on a grid. Each position is either floor, an empty seat, which is an L, or an occupied seat. For example, the initial seat layout might look like this. Now you need to model the people who will be arriving shortly. Fortunately, people are entirely predictable and always follow a simple set of rules. I wish that were the case. All decisions are based on the number of occupied seats adjacent to a given seat. One of the 8 positions immediately up, down, left, right, or diagonal from the seat. The following rules are applied to every seat simultaneously. If a seat is empty and there are no occupied seats adjacent to it, the seat becomes occupied. Okay. If the seat is occupied and four or more seats adjacent to it are also occupied, the seat becomes empty. Otherwise, the seat's state does not change. Every seat simultaneously. Floor never changes, seats don't move, nobody sits on the floor. So after one round of these rules, every seat in the example becomes this, because if a seat is empty and so let's run through these real quick. If a seat is empty, L, and there are no occupied seats adjacent to it, it becomes occupied. So that's this corner seat. There's no adjacent, there is an adjacent seat behind it, I guess, but okay, one of the 8 positions immediately up, down, left, right, or diagonal from the seat. So all of these seats are going to, this one has adjacent seats. If the seat is empty and there are no adjacent to it, so this doesn't apply. I don't think this first rule set applies to any of these, right? Because these all of these have a seat either up, diagonal, below. But we're gonna need to account for that in our puzzle input. Okay, so next one. If a seat is occupied and 4 or more seats adjacent to it, that also doesn't apply here. So why? Oh, the seat becomes occupied. So I think hang on. Otherwise, the seat's state does not change. Oh, okay, I misread that. There is no occupied seats adjacent to it. So this does apply. Okay. So that's why everything, this rule 1 is this rule 2 is not going to apply to this first round, but rule 1 is going to, because there's no occupied seats next to any of these. So they all become occupied. But then, if a seat is occupied and 4 or more seats adjacent to it are also occupied, the seat becomes empty. So then we have this case where so like this seat here has 1, 2, 3, 4 that are occupied. So that becomes unoccupied because of rule 2. 3 more rounds. Now this one, 4 or more occupied adjacent seats. So this one really only has 3. No, actually. Hang on. So this one, why does this one stay? This one stays unoccupied. Why is that? So 4 or more occupied adjacent seats become empty again. But then we have a case where a seat is empty and there are no occupied seats adjacent to it. I see. So that's why. This has occupied seats adjacent to it, so it stays empty. And it stays empty for a while. I think this one actually, yeah. At this point, something interesting happens. The chaos stabilizes, and further applications of these rules cause no seats to change state. Once people stop moving around, you count 37 occupied seats. Simulate your seating area by applying the seating rules repeatedly until no seats change. Okay, so we could have some kind of I think we almost need some kind of a state machine here, where like if there's no we compute the or we apply the rules and then we cache the previous application of the rules, and if there's no change, then we count the number of occupied. So we really only need some kind of enum value that represents empty, occupied, and floor. So this will be kind of similar to the tree one that we did. So we're going to need to read in rows, columns, and then we just need to read in these seats individually and have an algorithm on this, the state of this, and then check the map of the seats around it. Okay, so how do we want to model this? I already added the day 11 text and the day 11 full here. I think initially I'm going to have a like a layout type or a seat type that will be floor, empty, or occupied, and then we'll parse that into some kind of a multi-dimensional array of input like that. So I'm going to have an enum seat type it's going to be floor, seat, or floor, occupied, or empty. I don't know why this is thinking that it's used, because it's not. And then I'm going to have another one called the seat grid. And this will take in this is going to be a private val input, which is a list of seat type. And then I think I'm going to expose a method where I can get a seat at a specific coordinate. I'm going to have an x, which is an int, and a y, which is an int. It's going to be a function, and this is going to return a seat type. And I think I might abstract away some kind of like a seat rule that, because I anticipate they might give us some different rule that we have to apply in the next step. And so it would be nice to have that be abstract enough where we could go apply a rule to a specific seat. But I'm going to worry about that in a minute. So I'm just, for now, I'm just going to return input at x and then y. And I think this will be, I think what I'll do is like, this will be 0, 0, and then it'll go up as it goes along. So this will be 1, 0, 1, 1. So it'll be a Cartesian coordinates starting at 0, 0, and then increasing as we move down and to the right. Okay, so now I need to parse this. I have this handy method that I used here, there that I wrote in this test util. So I'm going to parse the input, and then these lines I want to map the lines themselves. And so I'm going to need to apply something to these individual characters here to convert them. And really we only need to worry about, in our input, did they give us, are there any occupied seats? So they start off completely unoccupied, so that's cool. We don't need to worry about that. Okay, so what we're going to do is, all right, add test. And we're just going to parse the input. Test util dot parse input, and then we want to just do day11.txt, and I think we're going to give it this class. I think that's it. Yep. And then the mapper, which is our method for mapping the lines, and we want a this is, we're going to just we can use this trailing closure in Kotlin. And then it dot map. So we're going to take the character, and then when it, we're going to have a when block. Oh, when, I'm going to have this be, I'm just going to have this be char, when char is a, we want to map the L to a seat type of floor. I don't know if seat type completely makes sense. It's more of like grid type, but I'm not going to worry about it too much for now. This is not fully add an else. I'm going to throw a runtime exception that invalid type. Whatever. Doesn't matter. We're not going to hit that case. So we want to map L to a seat type of empty, and we want to map dot to a seat type of floor, and then pound to a seat type of occupied. We're not likely to run into this. Like I said, the everything's empty at first, but whatever, it's worth doing. I think I'm going to make this into a private fun parse seats. And then this is going to give us that list of seat type. I might even go a step further and just have this return a seat grid. So we're going to do this, test util parse input. This is going to map the individual lines, right? This it is a line. And we want a map of rows, right? And then, oh, we actually want that. We can just do two list. That'll give us a list of seat types. And then we can just do toList. Okay, so val input is this. Test util parse input. And then we can just return a seat grid with this input. I just want to take a look at what this gives us, just to make sure that it checks out with this, that it jives with this input that they want us to have. Okay, so we got the seat grid. This grid is size 10, 2, 4, 6, 8, 10. Yep, that checks out. And then 0 is empty, floor, empty, empty, floor, empty, empty, floor, empty, empty. Cool. Okay, that's good enough for me. I might just glance at the second one. Most of these are empty except for floor. Okay, cool. So now we need to whatever, should not be null is what I'll say. And now we want to actually write our apply rules. And now is the fun part. So what I might do is have a method that returns a new seat grid and just applies the rules to it. And we want need to these ones. We might want like a private method to get the adjacent seats. That just gives us a set of adjacent ones. Because it's really, they're keying off of this for a lot of stuff. So we could get the adjacent seats as a set. If there's no occupied seats next to it, it becomes occupied. Okay. But first I'm going to write a method for apply rules. And then this, we want this to return a new seat grid. And the rules are basically going to be something that takes a seat. So we're going to have this be a seat type as input. Never remember this syntax, but we basically want a function that transforms a seat type to a seat type, and then returns a new seat grid. And then we're just going to say to do here. Syntax always higher order functions. That's what we want. Okay, so A is a C type. Oh, I see. Rules. The rules is this. It's something that that takes a C type as the input and then returns a C type out of it. And I might also expose, just for the sake of it, yeah, that method that I'm going to just do fun, get adjacent seats. And this just takes an x as an int and then a y as an int. And I might actually not need this. We'll see. So I'm going to write this method to get the adjacent seats of, let's try 0, 0 first. And so we basically want all 8 seats around it. So we want, like, if you have this one, you're only going to have 1, 2, 3, 4, 5 seats. Or no, that's not a diagonal. 1, 2, 3 seats. So we need to handle, if x is 0, I think I'm going to get a seat range. That's what we want. And this range of seats is going to be, we first need to get the x range that's valid here. So let's say x is 0. Well, then we're not going to, this has to be positive, right? So val x range equals so there's a couple cases we need to worry about. So these corners are, if x is 0, we can't have -1. If x is the length of this range here, we can't go over. So if x, I'm gonna do this. When x is 0, then we want a set of, or I'm just going to do a range operator. So 0.1. When x is the input 0.length, or .size, -1, which would be the last index here, then we want to do x -1 ... x. Otherwise, we want to do a range of x -1 to x + 1. Those are going to give us the ones around it. So let's say you have this one, it's going to give you this one and this one. And then val y range is when y is 0, we just want 0 and 1, same deal. When it's input dot size -1, we want y -1 to y. else we're going to want same deal, y minus 1 to y plus 1. And then we'll just do a for loop. I guess I will use this get seed at, which will give me that seed type. For I in X range, for J in Y range, and then I'm going to have my adjacent seeds, which is going to be this set. Adjacent seeds is a mutable set of seed type. I'm just going to do adjacent seeds dot add get seat at ij, and then we'll return adjacent seats to set because we want it to be immutable. And then it's complaining because the return type is invalid. So let's do that. Let's do let's write a test for, I'm not going to apply the rules yet. I'm going to do get adjacent seats. Val expected. So if we get the ones at 0, 0, I'm going to do this on a few different coordinates just to check that our boundaries are correct. So my expected is going to be a set of, it's going to be a set of floor, empty, empty. Whatever. So my grid, it's going to be the same deal. I'm going to get this grid. And then val actual is grid dot up dot get adjacent seats at 0, 0, and then actual, and we're just going to do a union of, or no, an intersection. I'm going to do actual minus, can I just compare it? Equals expected. I think I can just replace that with that. I think that'll work. So then let's see what that gives us. Hopefully it doesn't blow up. It did blow up. No tests were found. That's not true. Oh, I wonder if it's just this syntax is weird. No? Okay. That left corner, we'll say. What the hell? Method selector. Just delete all these. I don't know what's going on. There we go. Okay. So actual is true. That's not what we expect though. We expect that 1, 2, 3. This should have 3. Oh, we don't want it to be a set. Because a set only allows unique... A set will only allow unique things. So get adjacent seats should actually return a list. Because we need to count what we got. So we want this to be mutable list of this seat type. Okay, let's try that. Oh, interesting. So my actual is size 4. So actual gave me empty, floor, empty, empty. Wonder... Oh, I bet it gave me the X itself. Is that what happened? Yeah, that is what happened. Because I had 0 actually included in that list that I got back. So we don't want the X itself. So it's just, oh shit. So we do want, we need to subtract out the actual seat. That's going to be a problem for the Y and the X. Okay. Yeah, so what's happening here is I'm getting this X range, when I have 0, I'm getting this X range of 0 and 1. Which is fine on this line because we do want the 0 index here, but we don't want to actually include this seat itself. So we need to, we're going to do adjacent seats dot remove at, or we're not going to remove at, we're going to dot remove an element get seat at xy. And then we're going to do toList. toList. Oh, hang on. That is not a whatever operation. This is, it just removes. Okay. So then we're going to return adjacent seats dot toList. Okay. So now that should fix it. Yep, actual and expected are equal, so floor empty, empty. But that's not correct, is it? Because this should be, oh yeah it is actually, floor empty, empty. Okay, good. And then we want to do it, I'm going to test it at the right corner. We want to get the adjacent seats at y is 0, and then grid dot, hang on, I'm going to expose a method that's I'm gonna have a property called width. Val width is an int, and then the getter is gonna be input 0, 0, come on, 0 dot length size dot size. That'll be fine. -1. Okay. So what we're expecting in this other corner is that it's just going to be all empty. Just turn this off. Expected is empty, actual is floor empty floor. What happened? Did we get the wrong one? I think I might have. I think we actually want the width, grid.width. Let's see. Right. No, that's out of bounds. Index 10 out of bounds. Okay. Getting adjacent seats. Is that right? So the x is going to be this one, right? And we're expecting these to all be empty. Empty, empty, empty is what's happening. So our x range is 8 and 9. What happened? X range is 8 and 9. So that should be 0, 1, 2, 3, 4, 5, 6, 7, 8. Yep, that is correct. And then the y range is 0 and 1. Computing the y wrong? J and y range, 0 and 1. So if I get seat at at 9, that's empty, okay. 8 and 9, and then 1. The y range should be 1. Oh, I have these flipped, I think. So this first list is actually the y. So this inner list is the outer list is the y, right? So it's going down the rows. So we actually want yx. We got lucky with that first case because they were both 0 there. The adjacent seats should be all empty. Empty, empty, empty. Yep, that's correct. All right, let's make sure these all run. Okay, that's what we're expecting. Didn't like it. Didn't like it. Get adjacent seats at here. Oh, I see. I mean, they're not gonna be. Yeah, I mean, whatever. Actual is empty, floor empty. So we want to just make sure the actual dot size should be expected. That's expected dot size, and then they both contain everything. And we'll do this same test here. Okay. Oops. Now we should be able to run all these. Okay. Yeah, it's funny how like 80% of this, how much time have I spent so far? 40 minutes. 80% of this is just parsing this into the correct class and everything. So, but we're pretty close to being able to transform this. So I want to just do like a random, just some seat in the middle here. So like, we'll go 0, 1, 2, 3, 4, 4 over, and then 1 down. In the middle of input, we want this expected to be, we'll say, let's just say like 4, 4. Kind of in the middle of the input. So 0, 1, 2, 3, 4. 1, 2, 3, 4. We're expecting that to be 3, 4, 5, 6, 7 empties, and then 1 floor. One, 2, 3, 4, 5, 6, 7, and then 1 floor. I'm just going to say middle of grid. Okay. Yeah, so that worked. Okay, so our grid is feeling pretty solid at this point. So now let's try, let's just try applying some rules here. So let's just do our first grid is going to be this, and then grid dot apply rules, and then the rule is going to be get adjacent seats. And what we want to do is when we're applying the rules, we want to just blow this whole thing up. And apply to each of them. So I'm going to make a new input list, or val new input is a mutable list of, it's going to be the same deal. It's going to be a list of lists of seat types. And then at the very end, we're going to put that in a new grid and return that. Yeah. And then we could override equals for this grid and then have it, we'll just have it override, I mean, we have to override equals and hash code, but then we could compare two grids, and then once they stabilize, then we know that we're set. So we're going to do the same for loop for I in input dot indices. I'm going to say input 0 dot indices, and for j in input dot indices. Val seat is get seat pat ij. New input dot and then we're gonna, this is gonna be our, I think I'm gonna flip these. So I'm gonna do for j, for the y value, and then I'm going to make a row here. Val row is equal to mutable list of seat type, and then row.add, and then we're going to apply that function rules.invoke. I can just do this, rules, apply them to the seat, and then that will transform the seat based on what we pass in for these rules. And then I'm going to go for x, for I, and input 0.indices, which is our x's. Get seat at I, comma j. So this way we can kind of normalize around x and y being mapped to I and j. So we're getting the seat, we're applying the rules, and then we're going new input dot add, and then we're adding that row here. And then we're going to return a new seat grid using that a new seat grid using that new input. Yeah, so I think that'll work. So now we just need to write the rules. So we have our seat, and then we need to just return a new seat here. Seats. Now, and then we just need to get the adjacent seats, val adjacent. There's a knock at the door, so I'll be right back. Okay, so everything depends on the adjacent seats. So we want to do grid.get adjacent seats. Oh, but we don't know where we are we? Or do we? Shit. Maybe, I think instead of, we want the coordinates, is really what we want. We want the XY values of the seat. So let's do this, XY, and then we're going to do apply rules. We need to pass in this. The rules are going to be X, which is an int, and then Y, which is an int. Row.add rules ij. So we're going to do val seat is grid.get seat at xy. Adjacent seats, we need to get the adjacent seats at xy. then we need to, when seat, well, I'm going to just do if seat is empty, I guess the other way to store this would be as some kind of a linked list of seats. Or, yeah, I don't know, some kind of a tree that has the seat and the, or a map, maybe a map of coordinates to the adjacent seats, but whatever, it doesn't matter. And there are no occupied seats next to it. Then we want to adjacent seats dot contains a seat type of occupied. There are no occupied seats next to it. We actually want to do dot any. If any, it is a seat. Let's do none. Let's do dot none. There are no occupied seats. Then we return. We want to return a occupied. Now, if it's occupied, oh, I see. I think I'm going to do this as a single statement here. And adjacent seats are none. Then it becomes occupied. Else, if the seat is occupied and seat is empty, adjacent seats have occupied, else if else we just return the seat. There's no changes. I'm just gonna make this a little more clean here. I don't know, that doesn't feel more clean. So, seat type occupied. If the seat is occupied and 4 or more seats next to it are also occupied, count the occupied is greater than or equal to 4. Then we want to then it's going to be empty. I'm just going to do a static import of these. So our new grid is going to be that. And then new grid should not be null. Let's take a look at that. And then let's just compare it to what we expect. And let's run through these manually a couple times. There we go. New grid, we got this grid here. These are going to be occupied, floor, 2 occupieds. Yep, that's what we expect. And now let's try this again. New grid dot apply rules. I'm going to save this as val rules equals this function. Just need to return. Or I think I can just, oops. I can just return out of this here. And then we want seed type as this type, and then we can apply these rules. Okay. So now I can evaluate. New grid should not be null. And then we can do new grid dot apply rules. And then this third iteration, we have occupied. That's not what we want. These should have been empty here. Yeah, so something's up here. Let's run through this one more time. If seat is empty, if a seat is empty and there are no occupied seats next to it, adjacent seats, there are none occupied, okay, then it becomes occupied. Else if seat is occupied and 4 or more seats next to it, the count of occupied are also occupied. The seat becomes empty. So why did this not happen? Oh shit, that's why. It's applying on this current grid. It's not applying on the new grid. So we actually need to also pass in the grid itself. Yeah, that's why. Okay. So grid is the grid. Seat grid. That's why. Okay. So that was really confusing me. So in this case, this grid here is going to, I'm going to just call this first grid dot apply rules. And these rules, so it needs to grid is going to be this, or seat grid. Row.add rules, and then it's going to be this. It's going to pass in itself to this, and then we can work with it. Okay, so now that's out of the way. Now we can, this should work when we pass in the rules for the new grid as well. So first, this new grid is, let's just do a quick sanity check. Occupied, yep. And then when we do apply rules, now we have the rules applied to the grid. So occupied floor, empty, empty, that's what we expect. And then empty, occupied, perfect. That looks great. So now, now I think I might need to, just out of pure laziness and hunger, because I've been recording for an hour, I'm going to just expose a method on the seat grid that gets the list of seats. But I will expose it as an immutable map. I'm going to have an underscore here, and then val input is this list of seat types. I know this is exposing implementation details, but maybe I'll do a flat map. Val seats is, and then it's just going to be a list of seat type, and then this is just so I can compare the grids. I'm just going to flat map it. Input dot flat map it dot. Why is that not working? You know what? I'm just going to expose this, but I'm going to make it in an immutable fashion. So we're just going to make this a list of lists, and then we're just going to do input.toList. We're going to return a copy of it, and let's say count iterations until stable. Okay, so var unstable is Boolean. Unstable is a Boolean, and I'm gonna call it stable. It's Boolean, it's false, while not stable. Val new grid is I'm gonna call this current grid. Apply rules. Dot seats. Stable is this, and then the current grid is equal to the new grid, and then we iterate. This is going to be a var though first. Var current grid is new grid. Stable, we don't need this Boolean. Stable is false. I'm going to say iteration count equals 0. Var iteration count is 0, and then we just want to increment that. And then at the end, this iteration count should be, say, 27. And we just want to make sure that, oh, 3 more rounds. Okay, so I just want to make sure that our algorithm for this stabilizing method is is okay. So after one round, 1, 2, so this should be 5. 5 iterations should result in stability. So let's do that. Let's watch this work. Didn't like this. Count iterations until stable. Let's do this. Well, 6, whatever. It's close enough. And then now, it might have just been because we started after one round. Oh, okay. Second round, and then 3 more rounds. 3, 4, 5. And then it's on the 6th. It's on the 6th round that it stabilizes. So that is valid. Iteration count should be 6. And then we want to do new grid. Or current grid is the dot count. We got dot seats, dot flat map. This list of seats is going to be it dot to list. Come on. I do need to get all the seats here because I need to count I wish that the compiler could resolve this. It'd be really nice. Can I just do as sequence dot flat map? Does that work? This is super annoying. I've run into this before, and the compiler just gets really confused. Can I just tr to list? What about as sequence? Can I just do as sequence? I don't understand why that's not able to resolve. And then, but whatever. I'm going to do count, and then it is equal to seat type dot occupied. So ideally, I could just flat map this, count the number of occupied seats. Is this, and then occupied should be, after we're stable, it should be 37. Really wish it was easier to do this flat mapping, but doesn't like it. I don't understand it. It's obvious that I'm giving you a sequence here. And it's obvious, like, this is a list of seats, and so this should be able to, I don't understand why the compiler can't resolve this, but maybe I can help it out here. List of seat type. I don't know if that helps. No. Can I just map? Can I just manually flat map it? I guess I'll just, this is super janky, but I'm going to count it.toList.count this. Count row.toList.count, whatever. This is janky code. I'm not proud of it. So I don't know why it's not working. What if I just filter? Can I just filter it? Filter. I'm just going to do this and return true. True. How's that? You happy with that? No? No, you're not. This is really annoying. I wish I could flat map this. Can I just flatten it? Is that a thing that I can do? Okay. Now I have, okay, that's better. That's better, I like it. Cool. Okay, so now that should work. So I'm just gonna set a breakpoint so I can look at it. Cool, occupied count is 37. So now let's do the full input. Let's do it live, as Bill O'Reilly says. Count part 1. And hopefully this is not incredibly inefficient the way that I'm doing this. I am kind of brute forcing it. We're going to print the count, and let's do it. $37? That's, oh, what? Day 11 full. There's no way. There's no way that it's 37. Is he just messing with us? Day 11 full. Here's the rules. That's the wrong, yeah, that's the wrong grid. What's going on here? Oh, damn. Okay. File name. Yeah, I thought there was no way. There's no way that. Okay, 2,483 seats occupied. Let's submit that. Boom, it's the right answer. I'm gonna break this video up right now just because I've been recording for an hour, and then I'll do part 2 on a fuller stomach. So I'll see you in the next one.